Good afternoon, everybody. It's great to be back to Arkansas. I was trying to figure out the last time I was here. I think it was June or August or something like that, but it's always good to be back to my home state. And look, I usually talk a lot about myself at these kind of things, but I thought in light of, the events of the last week and everything that this would be more about a talk about hope. And I think that people have a lot of ideas about what science is, but for me, it represents probably the most powerful source of hope that we as a species have. Certainly, I hope that in some ways my life has demonstrated that, and will continue to demonstrate that, and make the lives of our fellow citizens better and push us out into the stars. So just a little bit of a background as far as who I am and what I've done for those that don't know my story. When I was about 10 years old, I found nuclear science and I found my passion. So, and that way I was just really lucky that, maybe I'm not that different than a lot of people, but I found what I loved to do when I was really, really young, and I just kind of went for it. I was interested in science all my life, and when I found nuclear science, I realized that this was something that I was kind of good at, and it was very, very interesting and very, very powerful, and I thought it could make a difference. So I built a nuclear reactor, achieved fusion when I was 14. That's the same reaction that happens inside our sun and all the stars in the universe, and for that matter, pretty much all the energy that we use today is born in a fusion reaction. Whether it's the energy in your food, which came from crops that grew with the energy from sunlight, or nuclear energy was originally locked up in a fusion reaction, and it was cool. I made this little star inside this reactor, and I still do a lot of fusion research, although I'm involved in a lot of things these days. But from that reactor, I went on to develop a bunch of different technologies. I developed nuclear security technologies to detect and interdict nuclear material in cargo containers, for example. I developed technologies that produce medical isotopes, so the systems that we use to treat and diagnose disease, many times use these radioactive isotopes, and I developed a way to do that basically in the hospital as opposed to in large consolidated facilities. And the majority of what I do these days, which is energy research, so actually figuring out how we transform our energy economy to do it in a way that can electrify the 1 in 5 people on Earth that don't have access to electricity, do it in a way that is safe and inexpensive and does not harm the environment and does not emit carbon into the atmosphere. And that's what I'm most excited about, and I think that's where the most opportunity lies in making a difference in the world. And to get back to what I opened with about hope, science is doing as adults what we all do as kids and children, which is exploring. As kids, we're all curious. We're curious about the world around us. We kind of poke and prod and get feedback from our environment. And, some of us in our careers have to kind of put away that curiosity and that exploration. A lot of us don't, but that's its heart of what science is. It's being explorers, whether we climb the highest peaks, whether we, extend farther out into space, or whether we probe kind of the heart of matter. It's exploration, really, that makes us human. I think it's in our genes that we are explorers, right? It was the the bands and tribes that went out and explored that were the most successful, found new resources, and in a way, that's the story of our country, was coming to a new world, a new land, in hopes that, it would hold riches and opportunities that exceeded those of the old world. And that's what science is, and it's an incredibly powerful tool for changing our lives. Now, part of what I do is basic science, studying kind of the heart of matter, what composes the universe, what are the forces, what are the constituents, and how can we use those to do different things. And part of it is the applied side of things. How do we take that knowledge of science and do something cool or interesting or beneficial with it, whether it's in medicine, whether it's in energy technologies. How do we take that science and try to make our lives a little better? And I do a little bit of a mix of both. I'm really lucky that I have the opportunity now to do basic science, and I have the opportunity to do the applied science and the commercialization of the ideas. And what I've found is there are very few problems that we face as a society, at least the big ones, that science can't at least in some way inform and try to solve. So just in that way, doing the energy research, lately the majority of my time is focused on power reactor technology. So these modular power reactors that can be built in a factory, shipped anywhere in the world. They can't melt down. They have no inclination to release radioactivity in the event of an accident. They emit no carbon in the atmosphere, and they need no fuel source for the operating life of the reactor. So what's so exciting to me about a technology like this is it offers this opportunity to kind of kill two birds with one stone. So you have, as I mentioned, 1 in 5 people on Earth that don't have access to electricity. If you think about it going forward, probably within 5 years, and if not that, definitely within 10, any point on planet Earth will have access to high-speed broadband internet, whether it's through projects that Google are doing with their balloons carrying aloft the transmitting capability, whether it's satellite efforts of satellites that are in orbit transmitting down high-speed broadband. I'd say within 5 years, any place on planet Earth will have access to high-speed broadband. And telecommunications and the internet revolution they've revolutionized our lives. What I did building a nuclear reactor, and keep in mind, really my career was self-taught. I was so passionate about nuclear science. It didn't feel like learning, but I was absorbing information from every source that I could find. And that would not have been possible without the internet, having those large databases and libraries of information, and just being an email or a call away from, world-renowned scientists, at least, the ones that would talk to me. And that was, that was the story of what I did, was having the ability and the access to the technology and access to the information. And so I think, if there's, over 1 billion people on Earth that don't have access to electricity, if they're going to have access to high-speed telecommunications, and then they have electricity. Think about how many people like me are out there that have the potential to do incredible things, make discoveries that make our lives better and improve quality of life. And that is a force multiplier on what I'm able to do. And so in that way, if we can electrify the 1 in 5 people on Earth that don't have electricity, and at the same time create an energy source that is lower cost and does not emit carbon dioxide into the atmosphere or particulate pollution, or has issues on the front end with mining or anything like that, I think we have a really positive opportunity for the future when it comes to energy. You hear about climate change a lot, you hear about energy security a lot, and certainly, these are probably, at least in the long term, the biggest issues facing our species. But we stand at this place with science where we've been given the tools to not only solve the problem of climate change and solve the problem of energy security, but do so while electrifying, the rest of the world in a way that you can't with current technologies. The developing world is not going to be building gigawatt scale power plants. They're not going to be building national infrastructure in transmission lines. They're not going to be building national infrastructure in oil pipelines or gas pipelines or coal access, at least not in the short term. And what alternative energy techniques, whether they're nuclear, whether they're solar, whether they're geothermal, provide us is distributed generation. This idea that you don't have to build these massive power plants that have pipelines going to them and then have to transport the energy, the electricity, thousands of miles. You can take and make energy in smaller production centers with smaller power plants. That is the model, that is the only model, in my opinion, that will rapidly electrify the rest of the world that doesn't have electricity today. And it's just, kind of sheer luck and a great opportunity that we can do that with technologies, the technologies that are distributed, that don't emit greenhouse gases, that don't emit particulate pollution in the atmosphere, that don't involve dangerous mining of the feedstock. So That's really what I see when I look out into the world, is this great potential for science to not only inform us as a population, teach us about where we came from and where we're going, and how better to understand our place in the universe, but it also tells us how we can manipulate the world for the better, right? I mean, if you think about it, the computer revolution, the petrochemical revolution, any industrial technology for that matter, came out of not a will to make a new product, but it came out of that exploration drive that's in our species, of just wanting to know about silicon, about the flow of electrons, wanting to know about this stuff that was bubbling up out of the ground and how we could use those building blocks to make new things. That was all just basic science. It was exploration, and it gave us these incredible tools that have given our species this incredible advantage over every other species on Earth, and given us the ability to ask these questions. And that's what, to me, is so inspiring about what I get to do, is the fact that we get to not only learn about the universe and do the thing that makes us human, which is exploration, but we can potentially solve the greatest problems of our time. And I'll just mention a little bit more about that, which is, of course, electricity is important, and doing that in a way that doesn't harm the environment is important. As the climate changes, it's not that we're going to get less rain in general, it's that where the precipitation happens will change. And in that way, water supplies have become one of the greatest resource challenges probably of the 21st century. If you think of the 18th century has been driven by ice, right? Ice was kind of a commodity that was in demand, and the 20th century being driven by oil. Perhaps at least the first part of the 21st century will be driven by water. You look at places like California, where they're depleting the aquifers, and the snowpack is not replenishing the aquifers as fast as we're using the water. And then you look at places in the world like the Gulf states, Oman and Qatar and the UAE. These are places where they have very limited food and water on hand at any one time. And for that matter, it's a security issue for them. If they were in a conflict and they had those supply streams cut off, they could starve to death. And so there is a great opportunity here in using energy as a commodity. Once it's low cost, once it's environmentally friendly, that is not your limiting resource any longer. And you can use energy, for example, to desalinate water. There's a lot of water in the world. We're really lucky as a planet that we have these great oceans and these great reservoirs of water. The problem is the vast majority of water on this planet is unusable for drinking and agriculture. But all it takes to make that into usable fresh water is energy. It's just historically, if you were burning coal or natural gas or some other energy source, it was either not cost effective, or it was not environmentally friendly to desalinate water for agriculture or drinking. And with my reactor technology and the other energy technologies that are on the very near horizon, we're going to open up an energy economy where energy is not the limiting resource. We can desalinate water at a lower cost than we can extract it from the ground or reservoirs. We will be able to make liquid fuels using carbon dioxide out of the atmosphere and water from the ground. If you think water has hydrogen in it, carbon dioxide has carbon in it. What's gasoline? What are liquid hydrocarbons? They're carbon and hydrogen linked together. And all it takes is energy. Now, traditionally, that energy has come from the sun, either in fossil fuels a long time ago, plants, and then they got compressed under rock layers, and then we suck it out of the ground. Or more recently, plants photosynthesize, create sugars, and then we use those sugars as our energy source. We can do the same thing, and we can do it more efficiently. We can take energy from a very dense, clean power source. We can take carbon from the atmosphere. We can take hydrogen from the water, and we can make the petrochemical infrastructure of this country, whether it's plastics, whether it's liquid fuels, from that in a way that doesn't harm the environment and is not resource limited. I mean, that's the other story. In the long term, if we continue to burn fossil fuels, we will heat up our planet. that is not a point of contention with anybody in the scientific community. We know that carbon dioxide traps heat. We've seen the trends. Now, we don't know which model it'll follow. We don't know if it's the one where we have 100 or 200 years of, pretty nice environment. It could be 5 or 10 years until things get really, really toasty and gnarly. But we know that carbon dioxide traps heat, and we know more heat in the atmosphere is more energy for storms. We know that the ocean level will rise. These are things that we can see in the models played out by the data. But that's only part of the problem, because along with more energy, more entropy in the atmosphere, we're burning up these resources. We will not have fossil fuels forever. Now, depending on the advancement of technology, these resources may last 20 years, they may last 50 years, they may last maybe 100 years, but for our species to exist long into the future, we have to have a sustainable feed source for our economies, whether it's energy, whether it's food, whether it's petrochemicals. And that's what these new technologies represent. They represent staying power for our species, right? The fact that they will ensure we're around hundreds of years into the future. And I think that's very exciting, and something hopefully I can have a part in developing these reactor technologies and developing materials that can be used in solar panels or batteries for storage, working with producing materials for electric cars, and all the other things. So that's a little bit about what I'm doing and why I'm hopeful for the future. And I guess I can take some questions if there's specific things people are interested in or want to hear more about. So, yeah.
Thanks so much, Taylor. If you have any questions, we can get a microphone to you. It's coming out. Start right there.
Yeah.
Hey, if I recall, I read, it's either a YouTube video or a magazine article about you where you were exploring the possibility of having a subterranean form of nuclear energy reactor.
Yeah.
And you didn't mention that when you mentioned the things that you were working on.
Yeah.
I'm kind of wondering what happened there, and if you could talk about its efficiency, its safety, the idea came from, that sort of thing.
So the power reactor technology is my baby. That's what I spend the majority of my time on. To me, it represents a transition to where we need to go. Fusion is the ultimate energy source, right? It is truly unlimited. We can suck the fuel out of seawater pretty much as long as we're going to be around on this planet. And it doesn't have any long-lived radioactive waste. It doesn't have any emissions into the atmosphere, and it's very dense. That's where we're going. We're not there yet. Fusion, I produced fusion when I was 14. Other people have produced fusion, but none of these things break even. They don't produce more power out than we put in. Who knows when we'll get to that point? It's potentially likely that we'll see that in the next 2 years or 5 years or 10 years, but whenever we reach break even, it's still about 10 years after that with the material science, the R&D on the power cycle engineering, all the things that go into making fusion a commercially viable power plant. So I set out to develop nuclear fission technology, which is the kind of technology that our current nuclear power plants are based on. Instead of combining light atoms, like happens in the sun, we take very heavy atoms that are already kind of unstable, things like uranium and plutonium, and we split them apart. And both those reactions release energy. Nuclear fission is a little bit easier to do because you kind of have to give it a nudge and it continues on from there, a chain reaction. You put in a neutron into uranium nucleus, it fissions, couple neutrons out, go on to fission a couple more uranium atoms, and the chain reaction continues. Now, that creates long-lived radioactive waste, and at least with the current slate of reactors, there are certain avenues in which accident scenarios can cause tremendous devastation in the environment, release of radioactivity and contamination of farmland, and we've seen that at Chernobyl with admittedly a really crappy reactor design. And then we saw that at Fukushima with a similar design to what's in this country, although a little bit older, in a very severe environmental catastrophe, natural catastrophe leading up to it. So nuclear power isn't perfect. It's very safe. So you have a nuclear power plant over in Russellville, Arkansas Nuclear One. Plants like that are very, very safe. They have very incredibly small risks of anything going awry. But that's usually at the expense of cost because you're building 2 or 3 power plants in one with the redundant backup systems to ensure that if anything fails, something will take its place to make sure that the reaction is always properly moderated and cooled, and even after the reactor is shut down, that the decay heat, the waste heat is properly rejected. So, nuclear power plants are safe, but they're not necessarily economically competitive. We're not going to be building thousands of new nuclear power plants, mainly because of the economics of it. These are gigawatt scale plants that typically don't meet their cost projections that the investors have been laid out to the investors. So what do we do? Well, I decided as a bridge to fusion, we could kind of take fission out of the 1950s, right? These reactor designs, light water reactors, were designed in the 1950s, both to provide propulsion and power for nuclear submarines and as the first entry of nuclear technology into the public energy sector. And they've been kind of incrementally improved. They've never had a radical rethinking, mainly because of inertia in the industry. So, looking from first principles, looking at the basic physics, right? Physics is the do's and don'ts of the world. Everything else, politics, economics, material science, it's all easy compared to breaking the laws of physics. So I looked at the laws of physics and saw what can we do, what's kind of the best case scenario, and how do we get there from here? So how do we develop the new materials it will take? How do we develop the new processes it will take in manufacturing and power cycle engineering? And that's what I've been doing. And it's a pathway that has a clear kind of runway to commercialization, and hopefully we'll see that relatively soon, certainly before fusion. And the nice thing about it is these power reactors prove out a lot of the concepts that make fusion a reality, right? They're very intense radiation environments, they're very hot environments, things you don't see in nuclear power plants of today. And you can almost drop in a fusion device in there to produce heat to supplement the nuclear power source. But the cool thing about the reactors is you have removed all the pathways to release radioactivity in the event of an accident. So you can shake the heck out of them, you can flood them, you can run away from them and say, I'm done with this, and come back in a month and no radioactive material will be released because they are intrinsically and passively safe. You design the system so that the inclination of the radioactivity is to stay in the reactor. And there's still some long-lived nuclear waste, although significantly less than current nuclear reactors. But it's certainly, I think, the right way to do things when you talk about making a carbon-free electricity source that is dense, that is environmentally friendly, and that is low cost. Because I'm a big believer in doing things for the right reasons, but realizing the realities of the situation. And the realities of the situation in the energy market is you can subsidize technologies as much as you want, but until the market wants them, they won't truly take hold, and they won't take hold in places like the developing world. And so what we need is an energy source that is competitive, or in many cases lower cost than fossil fuels, even hydraulically fractured shale gas. And that's when the market will be like, hey, we want this. And that's what this reactor technology represents. For me, I'm of course excited about that, but I'm also excited about some of the other potential opportunities of the reactor. For example, with spaceflight, I was interested in space exploration before nuclear science, and I thought I kind of had to give that up when I got into nuclear science. But if we're going to go to Mars, which I think we should, there's a lot of good reasons to go to Mars, we kind of need nuclear power, whether it's to get there, for propulsion, to cut the trip time down so the radiation doses of the astronauts don't get too high and they don't get too bored, but also power when we get there. One of the proposals put forward for doing a Martian mission uses what's called in situ resource utilization. So instead of taking all the fuel and oxygen and everything with you, you take what's there and use it. So there's carbon dioxide in Mars' atmosphere. There's actually a lot of water locked up in icy soils. And you can actually make the fuel for the return, the methane for the return mission. You can make the oxygen. You can extract the water. And you don't have to take that stuff with you. But you need these reactors to do it. And that way, I'm most excited about the reactors for that reason. Yeah.
One second.
On that note, I've heard arguments that the next target, rather than being Mars, should be the moon for human colonization,
Yep.
and then onto Mars. What's your take on that?
Yeah, so this is in the space community, a very controversial thing, right? So do we go to the moon first as a stepping off point, or we go to Mars? I think, me personally, looking at the very simple physics of it, the kinematics, and also some of the resource issues, I think going to Mars first is actually easier than basically going to the moon, establishing the resources there as like a fueling station or a jumping off point. I think it makes more sense to go to Mars directly. We can put resources into low Earth orbit to get them off the planet, and then utilize those as kind of your refueling station or your supply outfit to go to Mars. I think that makes more sense. The thing about space orbital dynamics is things are always moving. So people say, with chemical rockets, it takes, say, 6 or 8 months to get to Mars, or 12 months, or 4 months, or 32 months, or however long. And partly the reason for all those discrepancies is the fact that things in space move, right? There is a very good time to go to Mars, and there's a very bad time to go to Mars, depending on where we're aligned in our orbits. And for that reason, you have to carefully schedule when you're going to go to Mars. And that's part of the reason why it makes more sense to go from low Earth orbit to Mars than from low Earth orbit to the moon and then to Mars, in a kind of supply depot Martian architecture. The moon still has some interesting stuff. There's helium-3 on the moon, which is a fusion fuel, although I personally don't think there will ever be much of a market to go to the moon, mine helium-3, bring it back. It's just not a dense enough resource and it requires too much energy to expend there. Asteroid mining is something that's been proposed. I think from a scientific standpoint, we should go to asteroids. From a resource utilization standpoint, maybe for doing things in space, I still think in the foreseeable future, the long-term foreseeable future, 100 years out, 150 years, the technology still doesn't make sense to go to asteroid, mine its resources, and bring them back. I don't really see any resources on Earth that are limited enough to do that. There's some things like heavy metals, like gold and platinum, that we don't have a whole lot of. But with recycling, we have enough. We're not going to run out anytime soon. The most dangerous occupation is that of predicting the future, and I've certainly learned that in my short career. So who knows where we'll be in 100 years or 200 years. I mean, that is both the inspiring thing about science and the just downright terrifying things about science. It is so freaking crazy how the pace of technological innovation. I mean, you even see it in your lifetimes. I have a relatively short life so far, 22 years on this planet, but look, Moore's law, right? Every 2 years, the computing power doubles, right? We're heading for one of two futures, and both of those futures is both exciting and terrifying. Either Moore's law continues, and we get computer technology that vastly exceeds the processing power of our own brains, or it doesn't, and it flattens out, and some of these predictions don't come through. But either one has a lot of potential and is fraught with a lot of peril. And the same goes not just for computing technology, but all technology. Technology has tended throughout history to follow exponential trends, and humans are linear thinkers, right? We think if this is going to happen, it's going to happen about the same rate. I get this car, and in 2 years, I'm going to kind of get a similarly increased car, et cetera, et cetera. And technology trends typically are exponential, and that's where human thought diverges from reality. We are very bad at seeing trends, and so we're in for a crazy ride, at least in my lifetime, and I'm excited to at least do my part to develop the technologies I think will, really benefit us as a society and move us forward and increase quality of life and increase innovation, and then we can, all sit back and write poetry and do science, and that'll be a cool future.
In the back. Right behind you.
Okay. Hi, my name is Xochitl Delgado Solorzano. I'm a second-year student here at the Clinton School. And I appreciate you starting your talk, giving us a little bit of hope in light of last week. But in that same vein, is there something that you worry about a little bit more now that you didn't before last Tuesday?
Absolutely. And I think no matter what part of the political aisle you're on, everyone will have those things that worry them about next 4 years, next 8 years, and for that matter, the entire future of this country. Look, I won't delve into politics too much other than to say this, which is that don't let facts go out the window, right? We're really lucky, and I'm really lucky in the field I'm in, that we delve pretty much exclusively in facts. We take data, we run experiments, we take data, we look at what the data tells us about that experiment, and we draw conclusions and move forward based on that. And my hope is that President-elect Trump and any future politician for that matter will evaluate the data and use that data to drive their decisions in a compassionate way, in a way that looks at slow-moving threats and not immediate threats. The difference in ISIS and climate change. That's not to say ISIS is not an issue. It certainly is. But it is an immediate issue, and it's easier for humans to address immediate issues than long-term issues. It's why the majority of people who live in Miami-Dade County believe not only climate change is happening, but it's an immediate threat to their way of life, versus people in Indiana may believe climate change is happening, but may believe it's not dangerous or imminent threat to their way of life, but it will be. I mean, that's just the nature of these trends. Now, I would love to be proven wrong, and I'm always open to be proven wrong, but the data has borne out the models in some ways, though the worst of them. So hopefully, President-elect Trump and all future politicians will take heed of that. They will look at the data, they'll look at what's happening, and make a well-informed decision. And it's so frustrating, especially in the climate debate, which that's just something, very near to dear in my heart, that's been affected by the last week. It should have never been a partisan issue. It should have never been a political issue. I can see why. I can see the interest that created it into a political issue. But what's amazing about, what I do and the hope aspect of it is we have an opportunity here. Converting our energy economy will create so many new jobs and lift the economy in ways that are unprecedented. I mean, fossil fuels did that. When we went from burning peat to produce steam and steam engines to the fossil fuel economy, the economy boomed. And for the 20th century, the economy was tied to fossil fuels. The people who produce fossil fuels and the cost of fossil fuels were the driving forces behind the economy. And in that way, so too will then be the next steps in energy. And we're just lucky they don't emit carbon in the atmosphere. So the more we can do to encourage those, unfortunately, jobs that are lost to automation, jobs that are lost to innovation, very rarely come back, no matter what you do, even if you decrease regulation or whatever. This is speaking specifically to people in the coal industry. But so is the path of human progress. We will always innovate to the next place, and if we can encourage industry to train those workers for the future industries of tomorrow, the better off we'll be, and we'll be able to reap the rewards of innovation and to try to mitigate the downsides. Yes, horse and carriage, buggy drivers, their jobs went away when we got cars, but I don't think anybody still wants to be, riding around in a horse-drawn carriage. So at least to get to work and in our jobs. So I think I'm still optimistic. Not as optimistic as I was before, but still optimistic, and I'll keep doing what I'm doing. And the only other piece of thing I'll offer on that is more people in the sciences need to realize their humanity, and more people in the humanities need to realize the sciences, and that so much you have this thing where we're all guilty of this. People who are going to get their degree in science shun off the humanities, whether it's public policy, whether it's art, whether it's history. They don't put enough focus into it, and people in the humanities do the same thing. Science in a vacuum is pointless. We have to understand the broader context of why we do our work, because if you just do science in the lab all day, that's fine, but if you don't know why you're doing it, or you don't understand the broader societal implications of what you're doing, you might as well not be doing it at all, for all I'm concerned. And for that matter, I think people in public policy, in the humanities, could have a better understanding of science. And that's one thing I hope to do in my career, is communicate science to the public, to policymakers, to politicians, and I think we'll all be better off for it. So, yeah.
Right here. And then we'll go there.
where did you get the deuterium and tritium for your fusion reactor? And do you think that an antimatter reaction could be used to kickstart a chain fusion reaction, just like firing a neutron into the nucleus of uranium is for fission?
That's an awesome question, and that is actually a question I've thought a whole lot about. First thing, where did I get the deuterium? So I didn't use tritium. It was a DD reaction. So the fusion reaction I was doing is combining two heavy hydrogen atoms together. Funny enough, you can order deuterium through a local welding supply company, from a gas supplier. If you do it in large quantities, there are some export restrictions, but if you're just buying it in small quantity, it's okay because it's not radioactive. It's relatively easy to get the starting point for a nuclear fusion reaction. Tritium's a little bit harder, but if you really want some, I can give you some tips off the record. Second part of that question, antimatter catalyzed fusion. Interesting. I think antimatter catalyzed fusion is more theoretically interesting than it is practically, at least today. It requires a lot of energy to make antimatter, so antiprotons or antiatoms or positrons, antielectrons for that matter, even though they're a little bit easier to make. It requires a lot of energy, and there are a few places in the world that can make large amounts of antimatter, and there has been some work to catalyze fusion reactions using them, but I haven't seen anything that says, oh, this is like such a holy grail of initiating fusion that it's worth the energy investment in making the antimatter for that application. There are some other interesting things. Have you ever heard of muon catalyzed fusion? Yeah, so that's actually really interesting. So there's these subatomic particles called muons that are the analog of the electron, which is the common particle, the one that flows down our electrical lines and produces the light and lights up this and everything else. And the muon's the heavier version of that, and if you put it into a deuterium atom or tritium atom, it will actually catalyze fusions. It will bring the atoms close enough together they fuse, and that's a catalytic thing because it continues almost in a chain reaction. But again, it's the problem of how do we make muons, and right now it's very, very hard to do. But in some ways, if we could do that, if we have better accelerators that can make antimatter or muons, we have better accelerators for cancer therapy. So that's the nice thing about what I do is the interdisciplinary nature of it. I'm not a physicist, I'm not a chemist, I'm not an engineer. I'm kind of all three, depending on the hour of the day. And that's really, I think, how I was so successful in that, I took a little bit of physics and a little bit of chemistry and used it to solve a problem, and a tool, which was nuclear science, and applied it to all these different fields. And you look at Nobel Prize winners, you look at the greatest scientific discoveries in history, and they're all rooted in that. Move to the edge of your field, or move a little bit out of your field. Be a physicist that does something medical, or be a chemist who does something in material science. It's ripe hunting fields for scientific discovery.
If we were to colonize Mars, could your technology help shield the radiation or simulate more gravity so that we could colonize it? And how urgent is it because of how climate change is turning out?
So that's actually a really good question also. Something also I've thought a lot about. Mars is a fascinating place. I want to go there. I don't want to spend the rest of my life there, but I want to go there. So radiation, as you're aware from that question, is the biggest issue we face. There's a few things happen when you go out into outer space, especially in zero gravity. We found recently that your vision degrades, so you actually kind of go blind. A friend of mine, Scott Kelly, just spent quite a bit of time on the space station, a year in space, and his vision decreased significantly. We don't know exactly why yet, although we have some ideas. Something we've known for a long time is that your bones, basically, and muscles waste away. You're not here on Earth, you don't realize it, but you're expending a lot of effort to walk around and everything, and in zero gravity, you push yourself and you kind of keep going. So it's really easy to move around in space, and so unless you're like really exercising, and even if you are, your bones waste away and your muscles waste away, but all these things are just kind of, they're kind of, annoyances, right? They're not like mission critical. Well, they're kind of mission critical, but if you mitigate them, they're not mission critical. The one that's like actually dangerous is radiation, right? I mean, it's kind of funny that we're actually going to be using nuclear power to reduce the radiation dose to people. But that's because once you're outside of Earth's magnetic field, it's kind of gnarly. Whether it's something outside our solar system or something within our solar system, the sun has a big coronal mass ejection, it gets toasty, and I like radiation. I like hunt it down. I was doing that this weekend up in northern Arkansas out looking for uranium, but even I don't want to be out there when there's a coronal mass ejection. So we got lucky. We've only sent humans outside of Earth's magnetic field, protective magnetic field, for really one purpose, and that was the Apollo missions to the moon. And we were just lucky that there wasn't some big event while they were out there. And even so, they got tremendous radiation doses. So we got to work on that. We can create artificial magnetic fields. That could help. We can't take up big shields because they're too heavy, at least right now. I think once we're there, we could do, the radiation doses are less than the transit, but even once we're there, we can build the habitable environments below the surface, and you only need, a few feet of regolith, Martian soil to block the radiation. So yeah, I think we can mitigate radiation. The only thing is we gotta get there fast. So if we could get there in like 3 weeks, theoretically we could with the reactors. I'd be all for that. The first trip's going to take a little bit longer, though. How important is it that we go to Mars? Well, another acquaintance of mine, Elon Musk, has said that the main reason for going to Mars is to ensure, maybe not the main reason, but his big thing is the reason to go to Mars is to ensure a future for our species, right? Eventually, an asteroid will hit us. Probably a planetary scale catastrophe will occur. If climate change doesn't get us first, if we get a handle on that and we can deflect the asteroids, eventually the sun will expand its layers out and fry us all. So there's some reason for the continuity of our species to be interplanetary. I think in the short term, don't give up on our planet yet. It's by far the best home we've got. It'll be a long time, if ever, if Mars is as good of a place as it is here, even with our problems that we face as a society. So let's work on Earth. Let's save Earth, and let's go to Mars because it's fun, right? It's in our DNA, and who knows what we'll find. I'm just so excited. I'm still convinced we're going to get there. The thing is, we've never brought anything back from Mars. Every experiment we've ever done on Mars, we had to design the experiment on Earth, figure out how to package it in at most something that's the size of a small car, and basically has a few hundred watts. These lights in here are taking up way more power than anything we've ever sent to Mars. And we had to plan our experiments around that. So, no one was sending these high-powered electron microscopes. No astrobiologist, geologist was going and looking at the rock layers. And that's what's exciting, because who knows what we're going to find? I mean, we're pretty darn certain that there was flowing water on Mars. And, once we get down in those ancient stream beds, who knows what we're going to find? It's cool. We should do it just for that sake, not because we screwed up our planet, because I think it's still savable. I'm pretty still optimistic about humanity, about our common good and our care for others and our planet. I think generally it's in our best interest to help others. At least deep down we know that, even if sometimes we don't publicly say it. It's in our best interest to help our fellow man, and in that way I have great hope in common humanity that if we realize a problem is urgent enough, or we realize enough people are being affected by it, that we will all come together and solve it. And there's not going to be, it's not going to cripple our economy. It's going to make our economy stronger and better, and our societies better and more, affluent and have longer staying power. So I'm excited about that. But great question. I segued way off your question, though. Mars is a cool place.
We have time for one more. Yes, sir.
Is cold fusion science fiction, or is it possible?
Well, science fiction, and it's so much as it's been reported in the media. For those of you that aren't maybe as familiar with cold fusion, it was this thing in the 80s. Pons and Fleischmann discovered, or claimed to discover, if you took deuterium, heavy water, and you electrolyzed it at room temperature, you could create fusion. Well, the story got blown out of proportion. Even if they had achieved fusion like they claimed they did, which they didn't, we tried to replicate it all over the world and weren't able to. The power density wouldn't have been useful. Now, maybe theoretically it could have been scaled up into something if it had worked. Cold fusion as a principle, though, theoretically is possible. There are ways to make fusion reactions happen at low temperature. Muon catalyzed fusion is one of them. That's one way that you don't have to heat up the atoms to incredibly hot temperatures. Basically, this is how fusion works. Atoms repel each other, right? Like charges. They fly apart. But if you get them close enough together, if you get the nuclei of atoms close enough together, there's another force that's even stronger than the electromagnetic force called the strong nuclear force that takes over. So if you get them close enough together, they'll suck together and they'll fuse. It's just really hard to get them that close. And how you get them that close is you slam them together very, very fast. Well, what is temperature? What is temperature? It's speed. Temperature is a measurement of how fast the particles in a medium are going. And when you get to the temperatures that are found in the sun, in my fusion reactor, in even fluorescent lights, you're getting close. Those are the temperatures, those are the speeds that are required to get them close enough together to fuse. Cold fusion would be a way to do that without heating them up, without making them go fast. And that would be a catalytic, muon fusion is one way. I think there's some ways that haven't yet been discovered, at least proven out. They're theoretical ways and things I would want to work on. We know that in the middle of Jupiter, for example, at least we theorize, the core of Jupiter is made out of this stuff called metallic hydrogen. Jupiter has these massive magnetic fields. In fact, if you look at the telescope at Jupiter, you might could see them. They have aurora, beautiful aurora, massive aurora, because charged particles are being trapped by magnetic fields. Another reason let's not go to Jupiter's moons anytime soon without having the proper protection, because it's hot. It's a lot of radiation from that. It's radiation belts. Anyway, digressing. Jupiter has a magnetic field. Why? Well, we don't think it's because there's molten metal swirling around its core like Earth. We think it's actually, there's so much gravity and it's under so much pressure that hydrogen has compressed into this form of hydrogen called metallic hydrogen, where the hydrogen atoms align themselves in this crystalline lattice, much like a metal. And that can conduct electricity, that can create magnetic fields, and theoretically, metallic hydrogen, or a similar form of hydrogen that's very close together, where the atoms are very close together, if you just nudge it a little bit, it could fuse. Now, that's just theory today, but it's one of the probably 6,000 research projects over the next decades that I want to pursue. So, cold fusion, science fiction, at least in the way it's been portrayed. But maybe in the future we can actually do it. So we'll see.
Taylor, thank you so much for coming back to Arkansas and to the Clinton School. Thank all of you for coming out.
You bet.
And you're welcome back anytime. Thanks again.
Thanks. Appreciate it.